Good morning, everyone. So we had been, for the previous few weeks, we had been learning about the various atomic model, and recently we looked into the Niels Bohr's atomic model, and we tried to discuss in detail the various features as well as the positive points of the model as well as the negative points of the model. Particularly, I want to bring in today's session two important facts that come from the Niels Bohr's atomic model. One important fact is that Niels Bohr considered electrons as particle. Okay, so that is an important thing. So to realize right now that Niels Bohr considered electron to be having a particle nature. Another important thing that Niels Bohr considered in his atomic model was that the consideration of orbits. So that means the electrons in a Niels Bohr's atomic model is revolving around a particular orbit. Okay, so that means orbit means we exactly know a well-defined path. Okay, so a well-defined path is what we know when an electron is revolving around the nucleus in an orbit. So that means we know exactly the path that the electron is taking while it is revolving around the nucleus. So these are the two important facts that come from the Niels Bohr's atomic model. And these two are also the major drawback of the Niels Bohr's atomic model. Why that is so? Because when we were discussing the failure of the atomic model, we came to the conclusion that the two of the important hypotheses that was brought in later on, the de Broglie's hypothesis as well as the Heisenberg's uncertainty principle, both were not well supported by the Niels Bohr's atomic model. So if we look exactly at the de Broglie's hypothesis, basically, as we know that it said that the matter exhibit both the properties, that is the particle property as well as the wave property. So Niels Bohr only considered the particle nature of the electrons. So that means the wave nature of the electron wasn't taken into consideration. So that is why the Niels Bohr's atomic model failed to give a larger picture about the atomic model. Another important thing is about Heisenberg's uncertainty principle. So according to Heisenberg's uncertainty principle, it is very difficult to exactly pinpoint the position or the velocity and hence the path that the electron takes while it's revolving around the nucleus. So that means this well-defined path that electron follows in a Niels Bohr's atomic model is not possible according to Heisenberg's uncertainty principle. So both the wave nature is couldn't be explained by the Niels Bohr's atomic model. Another is the well-defined path that is set by the orbits is not possible according to Heisenberg's principle. So that is why the Niels Bohr's atomic model failed. So that means we now need to consider the wave nature also, wave nature of the electron also, while we are considering the electrons. So that is why we need a new way of visualizing the atomic model. So in order to bring in the wave nature of electron, a scientist named Erwin Schrodinger in 1926 proposed a wave equation. And this particular equation is what is given here. Okay, so this particular equation, which is basically a second order partial differential equation. So it is dou square psi upon dou square dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m by 8 square multiplied by E minus V into psi equals 0. Okay, you don't have to worry about the complicacies of this particular equation. So basically, this particular equation is known as the famous Schrodinger equation. So basically, his name only, Schrodinger uh, wave equation, Schrodinger wave equation. So this is a very famous equation, and for this particular equation and many other phenomena concerned with this particular equation, this particular scientist is an Irish-based scientist. He was awarded the Nobel Prize in the 20th century, in the early part of the 20th century. Okay, so his work was very much important. So he, using this equation, okay, tried to explain the wave nature of the electron. Okay, so basically, if we look exactly at this equation, this psi part, okay, psi is known as the wave function. Psi is known as the wave function. So you remember when we talked about the Niels Bohr's atomic model, there was a nucleus, and surrounding it we have the various orbits, right? And these orbits were termed as the energy shells or the energy states or the stationary states. Okay, so now in the wave nature of the electron, each of these energy states is represented by a wave function, which is psi. Okay, so that is what is written here. So this particular wave function represents the energy levels or orbits in the Niels Bohr's atomic model. Okay, so from this particular psi function also give us an indication of probability of finding electrons around the nucleus. So far in the Niels Bohr's atomic model, we had been talking about a fixed pathway of the electron. So now, since we now take into consideration the wave nature of the electron, so that means we now don't talk about the well-defined pathway that an electron follows, but rather we will say now in general the probability, okay, of finding a electron in a particular region is what we are going to say from here onwards. Okay, so I'll tell you what do you mean by that. So just we don't have to worry about these equations, because these equations is just like a mention or in your syllabus. We are not going to deal with the derivations or any of the solutions connected with this particular equation. Okay, so you don't have to worry about this. Just just have a look at this equation. Okay, here you have mass, Planck's constant, energy, voltage, okay, potential. Basically V is the potential. Okay, so psi is the wave function, and these are not the you might have heard in mathematics differential expressions. So these are not exactly your differential expression, but these are called as partial differential expressions. So the physics people might be learning it more in their quantum physics, but the other batch students, you do not have to learn about it. So just keep this in mind. This complicated equation was derived by Erwin Schrodinger, and it is known as the Schrodinger wave equation. So that explains the wave nature of the electron. This particular equation is what now bring in the wave nature of the electron, which was not taken into consideration by Niels Bohr. Okay, now what is the importance of this particular equation? So if we look exactly this particular partial differential equation showing the wave nature of electron, when you solve this particular equation, you get some solutions. Okay, so when you solve this Schrodinger equation for a particular wave function, okay, psi is your wave function. So when you solve this for a particular wave function, you get many solutions. So which wave function you should consider depend upon these solutions. So if your solutions is having a finite value, then those wave functions we will take into consideration, and that will represent your various represent the various orbits in the Niels Bohr. Now you have to remember, now we don't talk in terms of orbits, but rather they represent a kind of analogous terminology, and that is called orbitals. Okay, Now, what is the difference between an orbit and an orbital? I'll just shortly tell you. But before that, I would like to bring into your notice one more important fact, and that is that the Schrodinger wave equation is actually giving us this particular quantum numbers, which you might have studied in your 11th and 12th, where you talked about the principal quantum number, angular momentum quantum number, magnetic quantum number, and magnetic spin quantum number. Okay, so these four quantum number, basically the first three, the principal, angular, and the magnetic quantum number, they are a direct solution. When we solve this Schrodinger wave equation, we directly come to these particular values, and this is a magnetic quantum number that we bring later on when we take into consideration the electrons that are filling up the various orbitals. So these first three principal quantum number is coming from the solution of the Schrodinger wave equation. So that is why Schrodinger wave equation is having such an importance, because that is the reason why you have all these quantum numbers which you have studied in 11th and 12th. Okay, now let's quickly look into what is the difference between an orbit and an orbital. So orbit, it is now pretty clear to all of you, since we have been discussing quite a lot of time about the planetary orbit. So here we talk about the electron revolving in a specified circular path, and that is referred to as the orbit. Okay, this was proposed by the Rutherford and then taken further into the Niels Bohr's atomic model. So that particular assumption continued there as well. Now, what is the difference between an orbit and an orbital? So when we talk about orbital, actually here we talk about a space, a region of space around the nucleus. So now here we don't talk about the exact or a well-defined path for an electron. So if we talk about hydrogen electron, so hydrogen has only one electron, so it is revolving around a particular orbit, so that would be called as the orbit according to Niels Bohr's atomic model. Now when we bring into the concept of wave nature of the electron, now when we say that what is the probability of finding that one electron in this particular region around the nucleus. So if we suppose take the picture of the electron at various instances and try to put a dot for each electrons, then this picture would be looking at after a long period of time, we combine all the pictures. So the electron density will be at various positions in space during the time. So when you combine all the dots, it looks like the electron had been at various positions around the nucleus. So it is like a region of space surrounding the nucleus that is actually having the electron. So now we don't talk about the electron existing in a particular orbit, but rather in a region of space. So orbital represent the region of space where you find the probability of finding an electron. Okay, so orbital represent a region, orbit represent a well-defined path. So the current atomic model, since we now take into consideration the wave nature of the electron, so therefore now onwards we talk about orbital. So the orbit term now no more we use. We always talk in terms of orbitals. Okay, so orbitals are basically the region of space around the nucleus where you find the probability, where there is a probability of finding the electron. Okay, so according to the density of the spots, you will know where exactly there is more probability of finding the electron. Okay, so you might have talked about the s orbital, p orbital, d orbital, f orbital. So these are basically the region of space around the nucleus, and they have certain directional properties, and these regions will be having your electrons. Okay, so now onwards we will be talking in terms of orbitals and not in terms of orbits. So in the next video I will discuss some of the differences between the orbits and the orbitals. Thank you very much for your attention.